Hello, everybody. It's Mrs. Pound, and this is the second and final video for Chapter 37 on electromagnetic induction. So, our objectives for today's video are to describe a transformer and how it works, explain why transformers are used for transmission of electric power, and to explain how the electric and magnetic fields of an electromagnetic wave regenerate each other so that the wave pattern moves outward. So, let's first talk about transformers. So this is a transformer in the background. It is a device for increasing or decreasing voltage through electromagnetic induction. And it is a device that uses two coils around an iron core to change the voltage across a circuit. And so that's what a transformer is. Now, what it does is on this transformer, you'll notice that there are coils around both sides, and there is an iron core. Okay, electricity goes into one coil. These coils do not touch. It induces a voltage in the other coil. Okay, and it actually can change the voltage. And so how this works is if electricity goes in one, let's say it's a battery, when I first hook up the battery, you'll notice if you were attached a voltmeter to the secondary. So the primary is the one that goes in first, the secondary is the one that's induced. Um, we would find that there is a voltage induced in the secondary. And also when it is unattached from the battery, it's not continuous because there has to be a change in the electrical fields and the magnetic fields in order for there to be the induction. Okay. And so it has to be switched on and off. So this is where alternating current comes in, and that one reason our power transmission, because of the use of transformers, uses alternating current as well, is because there's a constant switching back and forth. So there's a constant change in those electric and magnetic fields. And so then we don't have to have mechanical switches switching on and off. It's the current itself that does the switching and will cause the induction. So that's another reason we use alternating current. Now, there are types of transformers. There's a step up and a step down transformer. In a step up transformer, there's a greater number of turns on the secondary than on the primary. So if this is the primary, it would have fewer turns than or coils than the secondary. And so what would happen is they call it a step up transformer because let's say the primary has one turn and it has a potential of 1 volt. Okay. If the secondary has two turns, then what would happen is it would induce a voltage of 2 volts in those two turns. And so it's called a step up because it ups the voltage. So underline step up and put an up arrow with a V for voltage. Okay, underline step up arrow V for voltage, so that you know that step up means that it's upping the voltage. Now in a step down transformer, there are fewer turns on the secondary than on the primary. So that would be the case where let's do it backwards. There are two turns of 2 volts on the primary. Now remember, these are not touching, and it would induce a voltage in the secondary of just 1 volt. Now I don't think I mentioned this. The reason for the iron core is that just intensifies the electric and magnetic fields. And so you could do this with just two coils and not have that magnetic core, but it does intensify the fields. The other thing I want you to do here is underline step down, put a down arrow and a V for voltage to show that the voltage goes down in a step down transformer. Now, the mathematical relationship between primary and secondary voltages with respect to the number of turns is the primary voltage over the number of primary turns. And so 1 with a degree sign is shorthand for primary. So you could actually write that for primary up above either, as long as you know what that means. equals secondary voltage divided by number of secondary turns. So it's a simple proportion for this. So an example of a problem might be the voltage across a transformer primary coil that has 100 turns is 20 volts. What is the voltage across the secondary coil, which has 20 turns? So we would put 20 volts in over 100 equals X over 20 turns. Then we would cross multiply. So 400 volts equals 100X. X equals 400 volts divided by 100, solving for X. So X would be 4 volts. So we have fewer turns, we have a step down transformer, fewer turns, lower voltage. Now, let's talk about some practical things with this too here. A step-up transformer cannot produce more energy than you put in. It sounds like we're producing maybe more energy and less energy. No, we're not, because we have to follow the law of conservation of energy. If a transformer increases AC voltage, the power will stay the same because power equals current times voltage. So if we up the current, we have to lower the voltage. If we lower the current, we up the voltage. There is conservation of energy here because we were saying power is energy when we're talking about electricity. If a transformer decreases AC voltage, the power still stays the same. It's the current that changes. If a transformer increases AC voltage, the magnetic field strength will also stay the same. And if a transformer increases AC voltage, the current will decrease. And vice versa, if we decrease the voltage, the current increases. The principal reason most electric power is AC rather than DC is because it is easy to step up and down the voltages with a transformer which must use AC. For that reason that we don't have to have the switches back and forth all the time. It's just really easy to do. So let's talk about power transmission. Another reason we do this is because power is transmitted over great distances at high voltages and low currents because higher current would heat the wires and cause large energy losses. When we were using the batteries in class, remember how quickly they would get hot and how hot the wires would get? That's because we had high current and low voltage. So we switched that around and we get a lot less heat, a lot less energy loss. And I imagine if there was heat, there would be some fires, maybe from leaves getting caught in there and things. So safer as well. Okay, and our last thing we're going to talk about is induction of electric and magnetic fields. So, according to Faraday's law, an electric field is induced in any region in space where a magnetic field is changing with time. So, if you have an electric field, it produces a magnetic field at that is perpendicular to it at a right angle. Now, according to Maxwell, a magnetic field is created in any region of space when an electric field is changing with time. So, the exact opposite can happen as well. So if we put both of those together, we get an electromagnetic wave. An electromagnetic wave consists of an electric field vibrating at right angles to a magnetic field. So a magnetic field will produce an electric field at a right angle to it, which will then produce an electric field, which will produce a magnetic field, and they just keep doing that at right angles to one another. That is why electromagnetic waves do not require medium. They can travel through space. And I also, just to wrap up this, um, this is just one of those things that really points me to the fact that there has to be a creator, there has to be God, because I just don't see how this could have happened by accident, okay, in our universe. Um, just where would something like this come from if it was not created and created to get energy to us on Earth from the sun, with the vacuum of space between us and the sun when we don't have other waves that do this? So this is one of those things that points, I believe, to a creator and to God. And finally, electromagnetic waves in space travel at a speed of 300,000 kilometers per second. That is just really fast. That is why radio communication is so fast. Now, over the distances of the universe, there are delays. So we get things like our light year, where it takes light a year to get to us from that distance, and things like that. But on Earth, this produces incredibly fast communication because remember, radio waves are in a form of electromagnetic wave and also gets our energy from the sun to us very quickly in about 8 minutes. So don't forget your 5 questions, and that's it for this chapter.